Hi, and welcome to CSI-RAShi, which is a distributed key generation scheme for C-side. This is joint work with Wout Billens, Lucas Disson, and Frederik Verkouteren, and my name is Robbie Pedersen. CSI-RAShi is a distributed key generation scheme based on Shamir's secret sharing and instantiated with super singular isogenies. In the quantum random oracle model, CSI-RAShi is robust and actively secure. But CSI-RAShi is also a Japanese dish that loosely translates to scattered or distributed sushi. The goal of this presentation is to introduce the main ingredients of CSI-RAShi and to show how they come together to prepare this delicious scheme. We start with very hard homogeneous spaces as a basis on which we can base cryptographic security. Then we use Shamir's secret sharing as a way to distribute a common secret among multiple parties. In order to achieve robustness and active security, we introduce a new primitive which we call piecewise verifiable proofs that will allow parties to verify that a share given to them is correct. And finally, CSI-RAShi will also need some standard zero knowledge proofs. So let's start with the basis. Very hard homogeneous spaces are basically a theoretical framework to generalize cyclic groups in which Diffie-Hellman type assumptions are hard problems. Instead of giving a full definition here, I rather compare them to elliptic curve points and show that they have quite a similar feel to them, but also some important differences. Remember that elliptic curve points form a group under addition. Over these points, we can define a multiplication map that takes a scalar a from Zn and acts upon a point P by the a-fold addition of P with itself. N here denotes the order of the group generated by P. In the very hard homogeneous spaces setting, we have a similar setup, but instead of a ring acting upon a group, we have a group acting upon a set, E. Typically, this group action is denoted with a star. But since G, the group, is cyclic, assume that we know generate a small g of it. In this case, we can define a group action that looks very similar to the multiplication map in the case of elliptic curve points. Basically, an element A acts upon an element E from the set by acting with the 8th power of the group generator on E by star. While this action now looks very familiar, there are a few key differences to the elliptic curve setting. In the elliptic curve setting, for example, we can construct linear combinations of points or associate consecutive multiplications. In this setting, we even have pairings as a powerful tool. In the very hard homogeneous spaces setting, however, we have much less structure, since there is no addition defined over the set E. So we cannot combine different elements in E, and there's also no equivalent of pairings. The only thing we can do is to see that consecutive actions by two elements A and B is the same as the action of their sum. And this lack of structure will prove quite restrictive when working with these spaces later. Very hard homogeneous spaces allow to efficiently sample and compare elements from G and E and to evaluate this group action efficiently. The hard problems in this setting are also quite similar to the classical case. So we have, for example, the vectorization problem as a counterpart to the discrete logarithm problem, the parallelization problem as a counterpart to the computational Diffie-Hellman problem, and finally the decisional parallelization problem reminiscent of the decisional Diffie-Hellman problem. As the next ingredient, I will revisit Shamir's secret sharing, which allows multiple parties to have a share of a common secret so that only an amount of players over a specific threshold can reconstruct this secret. Shamir's secret sharing is based on the simple observation that k distinct points in the graph uniquely define a polynomial of degree k-1. If, however, we have one point less, there are infinitely many possibilities for the polynomial f, and we cannot infer any information about any of the other points on f. Imagine, for example, we want to extract information about the intersection point with the y-axis. Given a single point of a line, there are infinitely many lines passing through this point, but as soon as we add a second distinct point, there's only a single possible line with a clearly defined intersection point with the y-axis, which we call f0. And this concept basically translates to any degree. So if you want to reconstruct a polynomial of degree k-1, or its intersection point with the y-axis, we need at least k other points. So now, how do we compute f0 given such points? Let's look at a graph that defines a polynomial of degree 8. We assume without loss of generality that these points are at position 1 through 9 for convenience. So we are in possession of the evaluation of the polynomial f at positions 1 through 9. What we do next is to assign a weight to each of these positions. These weights are called Lagrange basis polynomials, and this is where the real interpolation magic happens. The Lagrange basis polynomials depend on the set of points used to interpolate and the position we want to interpolate to. In our case, we have the set S, which includes positions 1 through 9, or more generally 1 through n for some integer n. We want to interpolate our points to f0, so we will use the Lagrange basis polynomials with respect to 0, which we simply call Li for position I. Li at position I is defined by the product of all other positions j divided by j-1. This allows us to simply compute f0 as the sum of Li times fi for all positions I and s, or from 1 to n in our case. Remember that we need n to be larger than the degree of f in order to be able to reconstruct f0. Otherwise, we will not be able to get the correct result. Note that in our setting we are also working modulo n, which is the size of the group of the very hard homogeneous space we are working in. So therefore we also need j minus I, which is in the denominator of the interpolation polynomial, to be invertible. Finally, let's take a look at how we can use this to distribute a secret among multiple parties. So let's take a smaller polynomial of degree 3, for example, which is uniquely given by 4 points. So what we can do now, since we know f, is simply to add more points by evaluating it at different positions. In this case, for example, f has degree 3, but we know 7 evaluations of f. So now, with any 4 points, we can compute f0 using the Lagrange basis polynomials. And the relative positions do not matter, only that there are 4 or more points. Now, let's assume there are 7 parties, each assigned one of the given positions. Assuming each of these parties knows the evaluation of f at a single position only, so that any set of 4 or more of these parties are able to reproduce f0 by sharing information. But they can't do it by themselves, or they can't do it with less parties. 3 less parties will not be able to infer any information at all about f0. More generally, assume we have n parties, called players, and each of them is in possession of exactly one evaluation of a polynomial f of degree k-1 at their relative position. So player 1 holds f evaluated at 1, player 2 at 2, and so on. Then any subset of these n players that has at least k players is able to reconstruct f evaluated at 0 using the Lagrange basis polynomials, if f has degree k-1. So if we include the possibilities of malicious players, we do have to make further assumptions to this scheme. So first, any set of k-malicious players would simply be able to reconstruct and steal the secret f0. So a first assumption we have to make is that there are at most k-1 malicious players. Furthermore, for the scheme to make sense and basically to work, we would need at least k-honest players that can reconstruct f0. So we have to add these 2 assumptions to the scheme, and this might seem a bit restrictive, but basically this is what's called an honest majority setting. And it's an assumption that we also make in democracy, or more importantly in Bitcoin, consensus mechanisms. We therefore call schemes of this type an honest majority kn threshold scheme, where n stands for the number of participating players, and k stands for the minimal threshold of players needed to reconstruct the shared secret f at 0. Now, an important question is, how do these players get their share of a common polynomial? Because basically, if somebody would generate a polynomial f and give it to every player, or give a share to every player, the generator would also know the evaluation of f at 0, and therefore know the secret. So, a standard solution to this is to assume that there is a trusted third party which generates f and simply distributes shares to every player. Unfortunately, trusted parties first of all need trust, which is hard to come by these days, and secondly, it will also introduce a single point of failure to the system. So, rather than use a trusted third party, we can use the following clever scheme. So player 1 takes the role of the trusted third party and generates a polynomial called f1. Then evaluates it at all positions related to parties 2 through n and sends them their share. Then player 2 does the same, and it generates its polynomial f2, it sends all the shares to the other players. And then player 3, and then so on and so forth, until every player generated their own polynomial. Now at the end, every player knows the evaluation of all n polynomials at their own position. So for example, player 3 knows the evaluation of f1 or f2 at position 3, but not at any other position. Now the trick is that we define the shared polynomial f simply as the sum of all of these polynomials. Now every player is able to compute the evaluation of f at their own position, and thus holds a share of the common polynomial f. And note that the sum of all of these polynomials still has degree k-1, so any subset of k players can still reconstruct f at 0. But note also that no player has any information about any of the other positions. I mean, player 1 might know f1 at 0 or at any other position, but since all of the other players added their own polynomial to f1, player 1 has no more information about it. Let's see how this looks like in a 4-5 threshold setting. Remember that 4-5 means that we have 5 players and that any 4 can recover the secret f0, so we are working with polynomials of degree 3. In a distributed key generation, every player generates their own polynomial of degree 3 and sends the correct share to each player, but no player sees any other polynomials. So basically players see this at the end. For example, player 1 sees these points and simply adds them up to compute its share of the final polynomial. And so does player 2 and 3 and so on. At the end, the players each hold a share of a common polynomial of degree 3 that none of them know, but that any 4 can interpolate to 0. Okay, so how can the players verify that their share is indeed correct without revealing it? How does player 1, for example, know that it has the correct share and that it was not given some wrong information by any of the other players? This is where one of our main results come in, piecewise verifiable proofs. So the idea is that the players taking part in the distributed key generation scheme want to prove that every other player has indeed received the correct share. Assume, for example, that player 1 wants to prove correctness of shares of f1 to every other player. In the classical setting, this can be done with so-called Pedersen commitments. Assume P is the generator of a group of elliptic curve points in which the discrete logarithm problem is hard. Then player 1 can commit to Qi, which are multiples of P by the polynomial coefficients of the polynomial f1 of x. Now, given these commitments, every player can verify if their share is indeed an evaluation of the polynomial f1 at their relative position by combining the polynomial coefficients in the exponent and multiplying them by powers of their position. Thus, each player can verify their own share, but is not able to gather any information about any other player's share, since they would need to be able to compute discrete logarithms. Yet, if all the players agree that their share is correct, since every player uses the same commitments, they all know that they implicitly share evaluations of the same polynomial. So this is great, but unfortunately we cannot translate these Pedersen commitments to the very hard homogeneous spaces setting, since we cannot linearly combine elements in the set E. The only power at our disposal are consecutive group actions. Thus, rather than committing to coefficients of a polynomial, we will have to commit to the evaluation themselves and then prove their correctness. The idea behind piecewise verifiable proofs is that the prover, in this case player 1, wants to prove correctness for each of the polynomial evaluations of its polynomial f1 at all the player positions 1 through n, and also at 0. Note that we can omit the evaluation at 1 since this is player 1's own position. So the naive idea is to simply commit to all of these values by letting them act upon an element E of our set, and then to use the sigma protocol to prove that all of these elements are indeed evaluations of the same polynomial. So to this end, the prover, or player 1, generates a random polynomial b of the same degree as f and then commits to b at positions 0 through n. The challenge of this protocol is simply a binary challenge, and in order to make the soundness error negligible, we therefore need to repeat the protocol multiple times, as indicated by the for loop, and lambda represents some target security level. So upon receiving the challenge, player 1 responds with the polynomial r, which is equal to b minus cf. Finally, we can verify correctness by checking if r applied to CFE is equal to the commitment. So if C is 0, r should be equal to b, and CF should be simply the identity map. And if C is 1, then r plus f should yield b, and the verification condition should also hold. So basically, since r has to be a polynomial of the correct degree, players can verify in this way that they all have a share of a common polynomial of the correct degree, and thus will be able to interpolate to a common value. And this protocol successfully provides that functionality, but has the big disadvantage that it costs skills with lambda times n squared. This is mainly due to the commitment step where we have to perform n group actions lambda times. So the second factor n comes in since every player has to complete this step, so we repeat the whole protocol n times. Since group actions, especially in the isogeny setting, are so expensive, we wanted to substitute them for a quicker commitment scheme. So we take a commitment scheme C that is quantum secure, so collapsing and quantum computationally hiding, and then we commit to the evaluations of B at the different positions via this commitment scheme. These commitments are then sealed by randomly generated values y2 through yn and can only be opened again using these values. Note that we don't do that at position 0, this is because we need the specific commitment later. So this will already greatly reduce the computational cost of the scheme in terms of group actions, but now we cannot rely on the same verification conditions anymore. I mean, they still hold at 0 since we are committing via group action, but for the other commitments this is no longer the case. And there are now two things to realize at this point. So first, since we are not committing to B via group actions, then there is also not really a reason to commit to F at these positions either. Second, while we have actually committed to the values of F1 at 2 and F1 at 3 and so on during the key distribution step, these are the values that we have sent to players 2 and 3 and so on up to player n. So we've actually already somehow committed to them. So now, since these players already know this specific value, we also want to give them the way of verifying them. This can simply be done by giving these players the openings to the commitments at their position. Thus, for example, we give player 2 y2 and we give player 3 y3, And then player I can, for example, open the commitment to be evaluated at I. And this finally allows player I to verify if its share of F is correct by checking if R plus CF gives the same commitment as B when committed using the same YI, or simply if R plus CF is equal to B. Thus, in this protocol, every player I is able to verify the correctness of its share as well as the evaluation at 0 of F. At the end of the protocol, if it was executed successfully, every player I then knows that they have a share of a polynomial of the correct degree that interpolates to F0 as was committed by the prover. Then, if all players agree that their share is correct and they agree upon F0, they will all know that they implicitly share evaluations of the same polynomial that has correct degree and interpolates to F0. Furthermore, no player is able to gather any information about any other player's share, since they cannot open the commitments without the extra information Y of the other positions. In the paper we present the non-interactive version of this protocol. Converting this to the non-interactive case is almost straightforwardly done using the Fiat-Shamir transform. Basically, we make commitments to the evaluations of B at 0 and at the different positions I separately, and we also give the opening Y0 for position 0 to all of the parties. Then we also commit to the statements via our commitment scheme C before hashing them to yield a challenge. The verification can then simply be done by player I recomputing the commitment at position 0 and I and verifying if hashing these commitments again gives the same challenge C. Note that typical zero knowledge proofs need us to hash the commitment scheme and the statement. However, we cannot really commit to the statements themselves, since F1 of I is secret with respect to any party that is not I. This is why we first commit to the statements before adding them to the hash, allowing player I to open the corresponding commitment. While this is not standard practice, we were still able to prove that using recent results on the post-quantum security of Fiat-Shamir, for example by Donfer, Mayens and Schaffner, that this does constitute a proof of knowledge in the quantum random oracle model. And also by using results of Unruh, we could also prove that the zero knowledge property holds in our scheme. So we end up with a tool that has similar powers to Pedersen commitments, which is that local or piecewise verifications allow to verify a global statement, which is the shared polynomial in this case, without giving any information about the other shares. In this sense, we can also interpret Pedersen commitments as piecewise verifiable proofs too. Yet, Pedersen commitments are technically not zero knowledge, since the prover reveals the commitments Qi of the polynomial coefficients. Now we have almost all of the ingredients for CSI-RAShi. So the first step in the CSI-RAShi protocol is the key distribution scheme based on Shamir's secret sharing. The idea is that every participating player I samples a polynomial fi of a previously defined or specified degree k-1, which is related to the desired threshold. And also every player samples a random element ri from the set E. The full implicit statement of this player is now that two given curves are connected by the action of its polynomial at position 0, and that the elements given to the other players are evaluations of this polynomial at these players' respective positions. So player I proves correctness of its statement by generating a piecewise verifiable proofs that allows players to verify correctness of the statements. The proof is given by a main proof pi tilde that includes all the commitments as well as the response. Next to the main proof, we have proof pieces Pij that include the openings for the commitments specific to the individual players 1 through n, as well as at 0. Finally, the prover publishes its Ri and the action of Fi at 0 on it, and also publishes the main proof and the opening at Fi0, and then sends the shares and proof pieces privately to the correct players. So each player would be able to verify the statement at 0 and their own statement corrected to their position. After every player has sent their pieces and published their proofs, the next step of the protocol is to verify these proofs. As said before, each player J then verifies each of its shares it's received at the relative position and at 0. This is done for all the received shares for all n-1 other players. If a proof of a specific player successfully finishes, then the other players know that they all hold a share of the correct degree of a same polynomial interpolating to a given value. If, however, the proof or a part of it fails, players broadcast a complaint against the player that distributed the shares. So whenever a player receives a complaint, it has to clear its name by opening the commitment of that player that filed the complaint for everybody to see. Everybody else then verifies if the complaint is justified. If players J's shares are indeed wrong, then the player I is disqualified. If a player immediately has k or more complaints, it's also disqualified in the honest majority setting. So after the verification step, players can finally complete their full share. Note that the audit may have disqualified some players, so we define the qualified set Q as those players who are still left. In the honest majority setting, there will always be at least k players, so Q is always larger than or equal to the threshold k. So finally, each player can compute their share as the sum of all of the shares of all the polynomials of the qualified players. And similarly, the shared secret is then simply the sum of the same polynomials but evaluated at 0. Finally, the last step of CSI-RAShi is to compute the joint public key. As said before, the secret key is simply the sum of all qualified polynomials evaluated at 0, and the public key is simply then defined by the action of this f0 on some starting set element e0. Note that the shared secret key is implicit and no single player can know it. So the question is how to compute the shared public key if nobody knows the action to perform on it. We already know that we can't simply combine different elements from the set E by addition or by multiplication, but we know, however, that we can perform multiple consecutive group actions. So the consecutive group action of f1 at 0, then f2 at 0, and so on for all qualified players is the same as the sum of all of these elements acting on the E0. So for simplicity, we assume that only the players 1 through some n prime are qualified. So what we can do now is to position them in the round robin and simply let each player compute the evaluation of their polynomial at 0 on the set element. So for example, P1 computes E1, which is the action of its polynomial at 0 to the starting element E0. Then player 1 sends E1 to player 2, and player 2 applies its action on E1, which returns also the same element as the action of F2 0 plus F1 0 on the starting element E0. This continues all the way until Pn prime computes its action. Then the sum of all of these actions results in the public key. Of course, this is provided that the actions of the players have performed are correct. Since at this point there might still be malicious players in the game, we want players to prove that the action they perform is indeed the action of their polynomial evaluated at 0. Thankfully, this is not hard to do, because remember that players have generated a curve R and published the action of their polynomial at 0 on the curve. Note also that this was verified by every other player, so we can safely assume that this action is at least correct. Then basically we want to prove that the action that the players computed from I-1 to EI in the round robin is in fact the same action that relates to two published curves. So for simplicity, we also call these curves Ri-1 and Ri. The player now wants to prove that the same action of Ei-1 and Ri-1 also yields Ei and Ri. So we can see this action in the diagram as component-wise. So in fact, we can achieve this by a standard binary sigma protocol as follows. The prover generates a random B and computes the action of B on Ei-1 and Ri-1, then basically receives a binary challenge. If this challenge C is 0, the prover simply reveals the left path, which is given by B, and if C is 1, it reveals the right path, which is given by B minus F at 0. So basically the response is simply B minus C times F at 0. So these are all the ingredients that we need for CSI-RAShi. Note that piecewise verifiable proofs and zero-knowledge proofs are what makes CSI-RAShi actively secure. Furthermore, having the specific setup, where we verify all of the shares before defining a public key, makes this protocol robust. So robustness basically means that the protocol succeeds even if malicious players try to foil or sabotage the computation. But of course, all of the security comes at a cost. Specifically for n players, the piecewise verifiable proof step now needs 2 plus n lambda group actions. Note that we assume any other operations than group actions to be negligible in comparison. The zero-knowledge proofs turn out to be much more expensive. They scale with 3n lambda group actions. This is mainly due to the sequential structure of the round robin and the many sequential proofs. Note that this formula is already optimized, so as players can use their downtime to already prepare parts of their proof. Finally, the total cost of the protocol scales with 4n lambda. Note that this represents the total sequential length of the protocol. The computational effort per player scales with 3n lambda, so basically the rest is downtime by the players, where they have to wait for others to finish. To get a clearer idea of the cost, we instantiated CSI-RAShi with isogenies. So in the isogeny case, the set E is a set of super singular elliptic curves defined over Fp, so a prime field, with an endomorphism ring isomorphic to an order in a quadratic imaginary field, while the group action on the elliptic curves is given by the ideal class group of the same order. So using the parameters from CSIDH 512, where the ideal class group has been computed recently, we find a time of 4.5 plus 18 n seconds for n players, assuming we have lambda to be 128. While this is not cheap, distributed key generation schemes generally only have to be performed once per operation, so it might still be worthwhile even if it takes quite long. To conclude, we introduced piecewise verifiable proofs as an alternative to Pedersen commitments in the very hard homogeneous spaces setting. Using these and standard zero-knowledge proofs, we were able to build a robust and actively secure distributed key generation scheme that is proven to be post-quantum secure in the quantum random oracle model if it's instantiated with isogenies. One main drawback is that the protocol is quite slow, which is mainly due to the sequential public key computation step that relies heavily on zero-knowledge proofs. So one open question is, of course, if the cost of the protocol can be further reduced somehow. Another drawback is that for the instantiation with isogenies, we need to know the underlying class group. So far, this class group is only known for the CSIDH 512 parameter set, which is quite far below the NIST post-quantum security level 1. So computing class groups is a difficult task, but on the upside, if large-scale quantum computers become a real thing, these class groups can actually be computed quite efficiently using quantum computers. Finally, we leave it as an open question for further research if these piecewise verifiable proofs are somehow usable in other applications. I want to thank you very much for your attention and enjoy your meal.